particular we saw the reflection coefficient. We saw that it depends on the parameters of the material, or the ground in particular, and let me give you some typical values that can be useful for real world situation. First of all, let's start with so-called poor ground, that means dry. We have conductivity and dielectric constant, that are the two parameters that are needed to calculate the reflection coefficient. And for this particular ground, the conductivity is 10 to the minus 3, and the relative dielectric constant is between 4 and 7. Those are standard values for this kind of ground. Then we have the average ground. The conductivity is 5 times 10 to the minus 3, and the dielectric constant is higher, 15. And eventually we have what we call good ground. When times 10 to the minus 2 and 25 is an electric constant. So very, very different. We'll have very different reflection coefficient. Then we have seawater. Much higher conductivity, 5. And much higher relative dielectric constant, 81. So it's not on the line, but close to the black hole. And last, fresh water. A very rather low conductivity, 10 to the minus 2. But the dielectric constant obviously is the same. Seawater is 81. So those are typical values that are used in doing your calculation. We will see that the reflection coefficient is very different with changing. In particular, when you go from dry ground to wet ground, the dielectric constant changes quite a lot. The electric properties, they change quite a lot. Okay, now we have talked about reflection coefficient. We know how to calculate the reflection coefficient. What do we do with it? We use the reflection coefficient to calculate the effect of a reflected electromagnetic wave. Starting with the so-called flat surface. We will move to a rough surface later on. Okay, let's imagine that we have a perfectly flat, smooth, reflecting ground, characterized by a reflection coefficient rho, whatever it is. And let's imagine that we have two antennas. That are located on two towers above the ground. HT is the height of the first tower, and we have a tower of different height, HR. The distance between the two towers, measured on the ground, is D. We want to calculate what is the power. T stands for the transmitter, R stands for the receiver, but things do not change if you exchange receiver with transmitter. So we choose this as a transmitter, this as a receiver. We want to calculate what is the power received when we transmit a given power. So it's a kind of link budget. But we will see that the results will be much more complex than the link budget in free space because of the presence of the ground. Okay, before we go on, let me say something that has been neglected. I draw the Earth as a flat surface. We know that the Earth is not flat. But the radius of curvature, if we approximate our planet with a sphere, the radius is 6,370 kilometers. If the distance d is small enough, and when I say small enough, I mean few tens of kilometers, 10, 20, 30 kilometers, something like that, then the surface of the ground of the Earth can be approximated as a flat surface. It's not flat. In fact, later on, when we consider longer links, we will remove this hypothesis. We will consider the curvature of the Earth. But for the moment being, let us imagine that the Earth is flat. So d is up to few tenths of kilometers. Okay, what happens? Okay, we have a direct electromagnetic ray. We call it RD, direct. And then we have a reflected electromagnetic ray. And we call this RE. please note that if the height of the tower is not the same, the reflection point is not in the middle. Because the condition, the Snell law tells us that those angles must be the same. So the reflection point will not be in the middle of the path. So as a first thing, we calculate those distances because we need them. Starting with the direct electromagnetic phase. This is easily calculated because this one here is a triangle and those are 90 degrees. So it's triangle, rectangle, I don't know what is Spanish. You can apply the Pythagoras theorem, very simple, and say that this thing here is the square root of d squared plus this height. This height here is simply ht minus hr. Square. Now we play a trick now to get rid of the square root because we divide everything by the square and bring this square out of the square root. Divided by the square. I just collected this square. Now this number for any link usually d is much bigger than the height of the towers because the towers may be high 50 meters, 100 meters, and the distance are tens of kilometers. So please remember that d is much bigger than ht or hr. So this ratio is much smaller than 1. It's a small number. Now there is a mathematical approximation that tells you that the square root of 1 plus x, when x is much smaller than 1, is almost equal if x is much smaller than 1. So it's an approximation of the square root. You can try it to believe it. So this thing here becomes hr squared with a good approximation. Okay, and we keep it like this for now. Now we have to calculate the length of the reflected path. This is easily done if you think that this geometry, if you look at this surface as a mirror, if you make a mirror image of this tower, this length here is exactly equal to this length here. I just flipped the geometry, the tower T, with respect to the plane. So it's easier to calculate this one because this thing here that I am now considering is again another triangle, another triangle rectangular equal. So this thing is the square root of this distance here, that is always d squared, plus this square, and this is ht plus h distance. Obviously, and this is always the case if you compare the two expressions, the reflected path is always longer than the direct path. This is natural. So we can do the same thing we have done before. So we take this square, we bring it out, divided by this square. And if we apply the same concepts seen before, we can approximate this thing with what do we do now? Now, if the distance is much bigger than both HT and HR, we can assume we can make some assumption on the difference of the path. In particular, let us calculate the difference in path length as the difference between the reflected path and the direct path. We want to see what is the difference between the two. Why it is important, it will be clear in a moment. Obviously, this is always longer than this, so the difference is always positive with that assumption. So if you take this one minus this one, what you find is d plus
Ah, claro, estás pensando que era PDF, acá, en el otro lado, el aéreo. No, pues son estos puntos de frecuencia.
and then we simplify 1D, so it's divided by 2D minus D minus HD minus HR is the same thing, squared divided by 2. Okay, so these things cancel out. And actually, a lot of things cancel out there. If you work out those equations, you know that this is HT squared plus and this is h squared you will find out that those terms cancel with each other, but those two terms, everything cancel out except what I've been circling there. And so this thing is 2HT HR divided by D. The difference path length has got that expression. So, if this is true, this number will be small with respect to D. This is obvious. If D is much bigger than those two, this ratio will be much smaller than D. It can be significantly smaller. We will do some exercises and you will see that this difference can be centimeters over path length of kilometers, but cannot be neglected. In particular, if this is true, we can assume that this difference is negligible as far as the amplitude is concerned. The difference between the two electromagnetic rays is so small that has no impact on the amplitude of it. But delta R cannot be neglected. As far as the phase is concerned. Why? You remember the expression of the phase. The phase of an electromagnetic ray is beta times R. So, and this beta is 2p divided by lambda times R. So what is important is the value of this quantity with respect to the wavelength. So this difference is surely negligible for the amplitude, but can be important for a difference in phase. Let me be precise. If you have a wavelength of 1 meter, if you have a difference in path length of 50 centimeters over 10 kilometers, those 50 centimeters of difference in length over a path that is 10 kilometers is negligible as far as the amplitude is concerned. But for the phase, 50 centimeters is half a wavelength. It is 180 degrees. So, as far as the combination of the two electromagnetic fields, it is extremely important. This will be clearer in a moment when we work out the equations, and will be hopefully clearer when we will be doing exercises. Questions so far? Okay, let's work out. Our objective is to calculate the receiving power. Okay, so we are working towards that objective. Okay, let's assume, just to be just to simplify our lives, let's assume isotropic antennas. So we don't have to take into account the antenna directivity function. And let's calculate the total electromagnetic field at the receiver. Once we know the total electromagnetic field, we can calculate the receiving power. We do this not in absolute, but we refer everything to E0, the electric field of the direct electromagnetic wave. So as a function electric field of the direct wave is the wave that you would have in free space. So this direct contribution here is the one that you would have in free space. So we just normalize everything to this value that is easy to calculate because we know the phase equation. So we can easily calculate this quantity. Okay, what will be the total field? Assuming that the electric fields are parallel to each other, so we don't have to mess with the vectors. We can write the total electric field as the summation of the direct field, the field of the direct wave plus the field of the reflected wave. And if you remember the definition of the reflection coefficient rho. We can express the reflected wave as a function of the incident of the field that we would have in free space times rho times and difference in phase that is due to the difference in path length. So we take only into account the difference take into account only the difference in phase between. So what we are saying here is that the reflected wave has the same phase of the incident wave plus an extra contribution due to the extra path. It's got to travel a little bit more. And the amplitude is the same apart from the reflection coefficient. That is, this extra path has no impact on the amplitude. Okay. Okay. Now, if let's simplify our life a little bit further. So if this is true, if D is much greater of HD, this should be enhanced. If this distance is much bigger than this tower, then the angle C would tend to 0, would be very small. Because the distance is very high, it is very big, so this angle will be very small, almost 0. Do you remember what we said yesterday about reflection coefficient? For very grazing incidents, the reflection coefficient in practice will be equal to -1. Both for horizontal or vertical polarization. We said yesterday, grazing and close. So we can even simplify our lives and write this thing. Delta phi, where obviously I called delta phi is the difference in phase, that is beta delta R. So I just a way to call that value. Again, if you have questions at any time, please stop me if something is not clear. Now, this complex number here can be written like this. We can use the trigonometric expression for the exponent. That is this is another way to write the exponent. As you possibly remember, this comes from this is 1. This is minus delta phi, that is this angle. This here is this complex number, and then you project, and you got cosinus minus iota. This is the real axis. This is the imaginary axis. So this is the same way to write this complex number. So we take this and we replace this there. And we end up with something like this. All those steps are necessary to develop the final expression, because what you will find is a very surprising behavior. And if you do measurements on site, on the ground, for any service, you will experience this kind of signal fluctuation that we will see in a moment. So unfortunately, those mathematics are necessary. Otherwise, you don't understand what's going on. Okay, now we really are interested into the absolute value of the total electric field, because this is what will be related to the receiving power. So if we take the absolute value of this thing, we get the absolute value of it 0 times the absolute value and this is very simply, so this is the real part of this complex number, and this is the imaginary part. So the absolute value is the square root of the real square plus imaginary square, so it's 1 plus and all this thing is under square root. Now this plus this is equal to 1. So you end up with 2 minus 2. Let me see where okay. Okay, now bear with me a couple of 5 minutes more, and we will arrive to the final result of this thing. This thing is equal to 1 minus cosinus di delta t is equal to 2 sin squared delta t divided by. So if we put this thing in here, the factor 2 can be collected, there is no big deal. We end up with a more useful relation that is okay, and this is the absolute value of the receiving field that you see is depending, sorry, okay, obviously this must be an absolute value, is depending on this parameter here. And now the next step that we will do is express this difference in phase as a function of the geometry. We already done that, but let's put it clear. Now, delta phi equals, let me write it somewhere. So. Now, delta phi was zeta delta f divided by cioè this divided by lambda divided by 2, and this difference this delta r was 2 ht hr divided by b. We are almost there. So you can simplify the things here. Okay, so far, apart from the, we are trying to, now we have an expression of the total electric field at the receiver as a function of the electric field that you would have in space, and this is easy to calculate, multiplied by something that has got in it all the geometrical parameters. Age of the tower, transmitter, receiver, wavelength, and distance. So the receive, we will see in a moment that the electric field at the receiver depends on all those parameters. For if you work at a fixed distance, it will depend anyway on the height of the towers and on the wavelength in a very peculiar way. To see this, we have to do a little bit more mathematics, but nothing special, just what is the receiving power?
I have a question.
Yes.
Where do you put the beta parameter in this expression?
Why? Because I made a mistake. Thank you. What is the receiving power? The receiving power is the effective area times the incident power at the receiver. Effective area, this thing is as you possibly remember, E squared divided by eta zero. So in place of the effective area, we want to use the gain of the receiving antenna, and so we replace it with lambda squared divided gain of the receiver. That's 0. And then we can do the square of this thing, that is 4. Nothing special, I'm just squaring everything.
One question.
Yes?
Why do you use for the effective area the gain of the transmitter?
I use for the effective area, I use the gain of the receiving antenna.
Okay, sorry.
So this is the effective area. Okay. Okay. But if you look at the link budget for we are talking about isotropic antennas. So for isotropic antennas, E0 squared divided by eta 0 is equal to the transmitted power times the gain of the transmitting antenna divided, if we can neglect the directivity function, in free space, that will be the expression of the power density of this quantity here. So we can replace that one in here, and please bear with me, we are almost arrived at the end of this process. So it's PT, gain of the transmitting antenna, E squared. Then it's lambda divided gain of the receiving antenna, 4 sin squared of this stuff. So you see that is much more complex expression than the one that we had in free space. This is the link budget for this situation. This is the receiving power as a function of transmit power. So this is the link budget when you have a reflecting plane. More complicated than the free space one. Now, we could easily take this equation and plot it and draw a diagram of the behavior of the receiving power as a function of distance or other parameters. So just to be specific, let me show you. I send via email to you the picture, so you should have the picture. You can annotate it if you want. Okay, what is this? Okay, this is the insertion loss, that is the ratio in dB between the receiving power and the transmitting power in dB as a function of distance for a typical 900 megahertz cellular system. Now the two antennas, the two towers are respectively 10 meters high and 2 meters high. So if you put that numbers in that equation and you calculate that equation in dB, that's what you get. You get the red line. The blue line is the free space link budget. If you were in free space, that's what you will get. You go on the ground at 2 meters above